Hey everybody, welcome to lecture number 2, the third lecture. Yes, I can count. Remember, we started at lecture 0, right? So that is technically correct. Anyway, okay, so what we want to do today is essentially figure out what two-dimensional kinematics is about, right? And this just means kind of figuring out everything there is to know about a mass moving, say, in the XY plane. So to begin, let's review by writing out the equations we had found previously for motion in the X direction. I'm just going to copy and paste these, and there they are, right, in all their glory. Okay, so notice now when I've written these, though, this time, right, I'm very careful to specify that we're talking about the X direction. And the way that I'm doing that is by writing subscripts after all the V's and A's, basically, right? And the reason that I'm doing this is because we're going to soon look at the y equations of motion. And we need, obviously a way to keep track of which component of the motion we're talking about. So I'm going to just say we can adapt these equations to motion in the y direction as follows. And so this is kind of new, but it isn't, right? Because all I'm going to do, as you can see, or as you will see, is just change all the x's to y's, right? You can see that these equations are all exactly the same, except everywhere I have an x here, I have a y here. Okay, and so this is perfectly valid, right? Because there's nothing really unique about the x direction. We said that from the beginning. We said we're just going to talk about the x direction for definiteness, but it really could be any direction, right? And if we wanted to, we could even write out the equations for the z direction, but we won't really have a need for that because projectile motion in particular can always be thought of as taking place in a plane, and so 2 dimensions will be fine for our purposes. So this kind of indicates, right? Well, let me put it like this. So assuming we know the initial position, and by this I mean the initial position vector, right? Initial velocity, again, velocity vector, and acceleration vector of the mass we're thinking about, right, as moving in the XY plane. There's no reason we can't write something like this. So I'm going to say the position vector is given by the ordered pair, right? And in the first position, we just have the x equation for motion. And in the second here, we have the y equation for motion. And I'm going to take this a step further. I'm going to use this column vector notation that I introduced in the 0th lecture. And I think that this makes it a little easier to look at, even though this is, I understand, a lot to write. But we can say then that we know, right after I just fill this in, again, assuming we know, the initial position vector, right, the initial velocity vector, and the acceleration vector, which we're, going to assume is constant, we now have, the position of the mass in 2 dimensions from this equation, right? And that's I don't know, that's powerful stuff. And so then I'm going to say similarly, we can write, and we're just going to do the same thing here, but now we're going to talk about the velocity of the mass. And what we will have is the y component of the velocity in the first position of this ordered pair, or sorry, I think I said y. The x component of velocity in the first position of this ordered pair, and the y component of velocity in the second position here. And once more, I'm going to use this column vector notation. And this one isn't quite as bad. It's just going to be the initial x plus a sub xt, right, just from the second equation in the first list there. And here we're going to have the initial y plus ay t. Cool. And so this is you know, pretty useful for us as people who are doing physics, because we'll see, you know, a little bit later on in the course that if we have the position and velocity of a mass, we have almost everything that we need to solve for anything that we care about in physics, right? It could be a force, could be the momentum, it could be the angular momentum, right? We can get all of those things just knowing the position and velocity of our mass at any given time. We also need to know the mass's mass, of course, because forces and momentum will depend on that. We'll see, you know, how that works later. But this is this is it, right? This is sort of what we've been building up toward. So hopefully this is okay. Let me see what I have next. I'll just put this in words to stress it, even though, or I'll put it in the document to stress it, even though I've said it, I think. But say that this suggests that if we know everything we need to know about the x and y components of the mass's motion, we can solve for any quantity of interest. And these will, for our purposes right now, namely be position and velocity, as is indicated by the equations I just wrote, right? And we can do this at a given time. Cool. So this might be a little bit shocking, right? I don't know how many of you have ever taken vector calculus, and you might expect that our approach would be a little more sophisticated than this, but this is really all we can do, right? It's just look at the separate components of motion for a mass, and then combine them, right? There's, you know, really not much more we can do. All right, so let's work an example. We're going to consider a point mass starting at the origin that is constrained to move in the xy plane. If its initial velocity vector has a magnitude of v naught equals 10 meters per second at an angle of theta equals 30 degrees above the negative x-axis, and its acceleration vector is constant with magnitude a equals 5 meters per second squared at an angle of alpha equals 45 degrees above the positive x-axis. At time big T equals 10 seconds, we want to find its position expressed as a vector and its velocity expressed as a vector. So the first thing I will do is just put in a quick sketch of what these vectors look like, because I think that will be useful. So let me just get that in here. So this is what they should look like. So just remember that this angle here, right, the angle that I'm calling alpha is going to be this angle, and the angle that I'm calling theta is going to be this angle here. It's hard to kind of get those into the sketch, but hopefully me just pointing this out is good enough. And so let's see here. The first thing, in general, when we're doing a two-dimensional kinematics problem, is to break the velocity and the acceleration. It's more often than not the velocity, but sometimes the acceleration too, as we need to do here, into their components, right? So let's find the components of the initial velocity and acceleration. So say that v initial x is given by negative v naught cosine theta, and v initial y is given by, sorry, this is going to be given by v naught sine theta. Okay, and I want to draw your attention to the fact that I've written a negative sign here, right? And this is because this vector lives in the second quadrant, right? Where its x component should be negative. And we're not going to have any issues because theta here, right, is 30 degrees. And remember what we were saying is that cosine of 30 degrees is going to be a positive number because it is between, it's definitely between 0 and 90 degrees, right? So this is correct. Hopefully you can convince yourself that this makes sense. And I don't think I'd really addressed that up till this point, so I just wanted to make sure that the reason for me writing this negative sign in here was clear. Okay. We don't really have to worry about that with the acceleration because both of its components are positive, right? So we can write something like the x component of acceleration is going to be given by a, this should just be cosine alpha. And the y component of acceleration is going to be given by a sine alpha. So that's good. Got that out of the way. And all it really comes down to at this point is plugging this information into our x and y equations, right? So for the x position, we have, and I'm going to copy and paste the equation from above here and just fill it in kind of. So we're all reminded what that looks like. So this is our x equation. Now we just need to put the information that we have in. So we're going to say x of t is, I think I said that this thing starts, yeah, it starts at the origin. So x naught is just going to be 0. The explicit expression for v initial x is going to be negative v naught cosine theta, right? And we have to tack that t on there. And then we're going to have that the x acceleration is given by a cosine alpha, and then we have to put the t squared in. And I'm going to just write this one more time. I'm going to clean it up a little bit. This step really isn't strictly necessary. And there you go. We have the x position of this thing at any time, right? Let me just do this. And then we just repeat the process for the y position, right? So for the y position, oh, that's how you spell it, right? I'll copy and paste the y equation. And we just fill this in. So again, we said it starts at the origin, so y naught is 0. We have that v initial y is just given by v naught sine theta. And then we just plug in what the acceleration is in the y direction, and that's going to be a sine alpha t squared. And then I'll clean this one up as well. This is going to look like v naught t sine theta plus 1/2 a t squared sine alpha. And that's it, right? Now we can write what say if we wanted to write it this way, we could write what our R vector is at any time. I don't even think I'm going to plug the numbers in because that's, well, I kind of want to start sort of gradually distancing myself from the numbers because I don't think that there's too terribly much benefit in solving for things numerically, if I'm being honest. And that's just it's just a matter of plugging into a calculator, right? And I trust that you can plug things into a calculator. So from here on out, I'm gonna sort of not emphasize the numerical results as much unless I think that they're important for some reason. So I'll just leave that to you. You just plug in, you know, T is big T, which is given by 10 seconds, and you can come up with a numerical answer for this. I guess I'll just say one more thing here. What we want to evaluate is this, remember, the full position at time big T, and this would just be given by x of big T and y of big T, like that. So this is what we were asked for, right? And it equals, you know, some number, whatever, who cares, right? Numbers, who needs them? So the process for the velocity is very similar. We'll go through that. So let me just say for the velocity procedure, very similar. And let's just start calculating, I guess. I'm going to copy and paste the expression for velocity as a function of time. Remember, it's this. And we found that the initial x velocity, right, was negative v naught cosine theta. And then we're going to have here, we're going to have plus a sub xt. A sub x was a cosine alpha, right? And I'll just write this one more time, clean it up a little, so this is not as bad as the position equations, right? So we have at cosine alpha. Cool. And then we just do the same thing for the y velocity. And we had the initial y component of velocity was v naught sine theta. And we had that the y component of the acceleration was a sine alpha times t, and then one final time here. And there we go, right? And I just will point out that what we were asked to find, right, was the velocity vector at the time big T. So that will be given by this. And this again will just equal some number, right? So there you go. We're doing two-dimensional kinematics. Isn't it exciting? All right. So let me just write a few words down here, just to sort of recap what's happened, what we've shown, right? So I want to say that this shows that if we want, let's say, the full picture of the motion of an object, we can simply analyze the x and y components of its motion separately and then, you know, combine this information, I guess, right? And that's what we just did. And we'll do a few more examples before this lecture is over. So hopefully it's becoming clearer, and hopefully it's completely clear by the time we're done. Okay, so on to, you know, it's the craziest thing. I keep wanting to pause to ask if there are any questions, but then I remember I'm recording. So I'll try not to ask. Okay, so let's talk about freefall, because this is an important sort of subtopic, right? And I'm going to put some words down in the document here. I'm going to say that when we talk about freefall, we're referring to an object whose only acceleration is that due to gravity. And we denote this with G, where, for those of you who like numbers, we can say that G is approximately 9.81 meters per second squared near the surface of the Earth. And so we can adapt our y equations to the free fall case by simply making the substitution that a sub y goes to negative g. So I'm going to copy the y equations of motion now and just substitute this in, right? So let me grab those. And I'm not going to really bother with this very last equation. I don't intend to make you guys use this very much. So, and also, you know, this doesn't have any acceleration dependence, right? So it kind of doesn't change. So there's a few reasons for me not to include it here, I think. So let's, plus it's less for you to write. So hey, that's cool too. So let's see what these end up looking like. This is going to become negative. I just take this to G. I have to remember to put a negative sign in here. Take this to G. On one more time, negative sign. This becomes G. There you go. We got the y equations for free fall. Aren't they glorious? And so there is more to it though, because we need to change the x equations as well, right? Remember that I just said the only acceleration acting on the object we're thinking about here is due to gravity. And so I'm going to do a little sidebar here and talk about air resistance, which we'll pretty much always neglect, right? So let me just say, furthermore, when doing problems involving projectile motion, to simplify our calculations, we'll almost always neglect air resistance. And we do this not only to simplify the calculations, but also because most of the time it won't make a huge difference. And you know, if we didn't do this, we would wind up with I want to say we'd wind up with a differential equation because we would have that. Well, air resistance in general depends on the velocity of the object, right? So it really does become more mathematically complicated. So anyway, this means that for our x equations, we take, and I'll say we just take, and this is nice, we just take the x acceleration is 0, right? So that's going to, you know, simplify these quite a bit. So let me scroll up here, copy those, and then change them as appropriate. And I will, again, not bother with this last equation as it also has no acceleration dependence. and I don't, foresee making you guys use it as I mentioned. So let's see what we get here. This whole term just goes away, right? This whole term goes away, and this whole term goes away. And it actually kind of seems like we don't really need this third equation here, because this is just something that follows directly from the second equation, right? Because if Vx equals V initial x, then obviously Vx squared equals V initial x squared, right? So we can just get rid of this, and we kind of see that there are only two equations in the x direction that we care about, and one of them kind of states, right, the second one kind of states something we just asserted, which is that there will be no air resistance, and thus the x component of velocity will be constant, right? So let me see what I have here. Yeah, so this is it for projectile motion, right? These are going to be the equations we want to think about, this set of equations and this set here. And I should just say that this is assuming that the y direction is sort of the vertical direction on the surface of the Earth, right? That seems probably pretty obvious, but there's no reason that y in the mathematical sense has to correspond to vertical, in sort of our everyday life, but that's the convention that will follow, right? I mean, if you're talking about three-dimensional kinematics, you could have, say, like x and y sort of be a plane, a plane on the surface of the Earth, and the z direction would then, give you your altitude, let's say, your distance above the surface of the Earth. But as I think I said, we don't have to really do three-dimensional kinematics, because this motion will always occur in a plane. We can always define a plane such that this motion is occurring in it, I should say. Okay, cool. Let's see here. Just want to make sure that there's anything. Oh yeah, there's a lot of stuff actually. Okay, so let's look at the implications then. So the implications of this are, and this is just to kind of summarize a little bit, but the first one is going to be the x component. We just said this, right? But I want to make a list. The x component of velocity doesn't change. Okay. The second implication is going to be that projectile motion is parabolic. And this just means that, if we look at the path that a projectile takes through the air, or I should say through space, it doesn't have to be through air necessarily. It's going to look like a parabola, right? That's kind of all this is saying, sort of, to just rephrase it, I guess. And before I continue this list, I'm going to put a quick sketch down here, and we'll talk about that in a second. But this is, sort of the prototypical projectile motion trajectory, right? It's going to be a parabola. Okay, and so this might not be immediately obvious, but I want to say also that the magnitude of the initial y velocity is equal to the magnitude of the final y velocity, with a qualification. Nope. There we go. With the qualification that the projectile is launched from and lands at the same height, right? And that's what we have in this picture here, for instance, right? We're talking about flat ground, and the projectile is launched from this, position over here, and it lands at the same height. In this case, the most obvious choice would be to just take both of the heights here to be 0. And that's often what we'll do. And so we could write this mathematically as we can say, i.e. that delta y equals 0, right? And so it's important to remember that this only applies if your object starts and lands at the same height, right? Okay, and then there's one more, and that is that the projectile's y component of velocity is 0 at its maximum height. And we can talk about why this is and sort of look at the sketch to help us understand. But what we kind of see, right, is that if we just think about the y velocity, is that it starts out at some value, its initial value, whatever that is, right? And as the projectile moves through its path, its trajectory, the gravitational acceleration is constantly pointing down here, right? It's always going to point towards the surface of the Earth. And so what that's doing is that's just taking velocity away. It's just sort of decreasing this y component of velocity as the projectile moves up until the y component of velocity becomes 0 at the maximum height, right? And then as the object begins to fall again, you know, from here to here, it's rising, and from here to here, it's falling, of course. And as it begins to fall again, then the velocity, the y component of velocity switches to become negative, and it gradually becomes more negative. And the length, let me say it like this, the length of this arrow here, right, is the length, is equal to the length of this arrow here. And that's what we said with implication 3 here, right, that that the magnitudes are equal. I think that's all the important stuff. I could say there's one more. Maybe let me just put this in. While I try to remember my Roman numerals, I think that's 5. The maximum height will occur. Let's see, when projectile's x position is half its total horizontal range, and I'll call this big R. So what I'm saying is that, and this actually, I should say that I'm just going to copy and paste this, because this is also going to depend on our delta y being 0. Or let me just say it more succinctly here, and that's again if delta y equals 0, right? And so this is, you know, kind of the symmetry of projectile motion here that we're talking about. And so this is important, or it could be important to remember, I guess. And I don't think there's anything terribly shocking about that, right? You know, nature likes symmetry, so cool. I think that hits kind of all the key points of two-dimensional projectile motion. I'm just going to wrap up with some examples here, and you'll have some more to do on your homework, so you can hopefully get comfortable with these ideas. So looking at an example, okay, so you're watching a baseball game, right? And for your favorite team to win, the quarterback needs to successfully kick a field goal. So this means that she needs to kick the ball over the goalpost at a height of h, well, big H equals 2.5 meters. And she's going to be kicking the ball from a distance d equals 15.5 meters away from the goalpost. And the ball is going to be launched at an angle of 30 degrees above the horizontal, right? So we need to solve for like what the initial velocity is that she must impart to the ball to make this happen, right? And so let's do it. And I'm gonna introduce a variable here. So let's call the time at which the ball is positioned just right over the bar, big T. And so this trips people up, and it can be a little bit tricky. So I want to kind of belabor this and hopefully make sure that it's clear for everybody. But this amounts to demanding that y of t equals big T equals h, right? So we're saying that at some time, big T, the y position of the ball has to be at the height of the crossbar, right? And you might ask yourself, well, isn't it just going to hit the crossbar and bounce off? And yeah, that is technically what would happen, right? But we can't, this is a limiting case that we're solving for. So we have to bear in mind that whatever initial velocity we solve for in real life, the velocity that we need would have to be just a little bit larger than that. But all we can really do is solve for this limiting case. And we're going to do this a ton in this class. So hopefully that isn't too weird for you. So anyway, we're just saying, okay, the y position at some time, big T, has to equal the height of the crossbar. So what we can do is we can just sort of write an equation that reflects this, right? So we can say y of t equals big H, and then we just plug in y initial plus b initial y t. And now remember, we're talking about projectile motion. So this is going to be minus 1/2 g squared. Okay, and we can, of course, take the initial position of the ball to be our origin, right? So we can say that the initial position of the ball is at x equals 0 and y equals 0. And with that, along with substituting in for the explicit representation of the initial y velocity, our equation then starts to look something like this. So we're saying y naught is 0. Breaking the velocity into its components, the initial velocity into its components, we would find that this, the initial y, is just v naught sine theta. And then everything else about the equation stays the same. Actually, you know what? I made a mistake. I apologize. This should be a big T. Just to be consistent. Probably not a huge deal for most of you, but I want to be consistent. So I'm going to clean this up. So there's no reason to have this 0 written here, I guess, right? Because it doesn't do anything for us. And then I just want to rewrite this as v naught big T sine theta. I think that it just looks nicer. And so there we go. We're kind of getting somewhere, right? Because we have this equation here, and there are two unknowns, right? There's the unknown that we care about, right, that we want to solve for, which is v initial, and then there's the unknown, which is the time, right, at which the ball is where we want it to be. And so at this point, thinking back to our algebra knowledge, we know that we're going to need another equation here, right? Because one equation with two unknowns isn't going to work for us. So we get that other equation. I'll put this in words, but at this point, we need more information. That information will come from considering I'll just say generally the x direction. And so let's come up with an expression for the x position of the ball as a function of time, right? And remember that our general expression, how do I want to say this? Well, let me write this symbolically first. So we're going to say that x at t equals big T. We're going to demand that this is d, right? Because that's how far she is away from the goalpost, right? And then we're going to do the same thing that we did. for the y direction. So that will be writing that x of big T equals x naught plus the initial x big T, right? This is one of the projectile motion equations that we just, I don't want to say derived, but we found, okay? And then actually I should put one more thing here. Remember that we're demanding that this is equal to D, right? That's sort of the crux of this argument. And so we can rewrite this equation now. Remember x naught, right? We said that that was just going to be 0 because we can always, to reiterate, choose our origin to be where we want it to be, as long as we're consistent with that choice. So that there's that just gets rid of the x naught there. And breaking the velocity into its components will show us that v initial in the x direction is just v naught cosine theta, right? And I would suggest that you make a sketch of this and convince yourself that this is the appropriate expression for the initial x velocity along with the one we use for the y direction. So what we find then is we find that d is simply v naught t cosine theta. And at this point, it's just a math problem because now we have two equations, two unknowns, and we just have to do the math. So the way we would do this is, there's a bug on my screen. The way we would do this is we would just note that, let me put this in words. To solve the x equation, the one we just found for t, and we plug this in to our one word, right? Into our y equation. So this is going to give us, let's see, t is d over v naught cosine theta. And from this, we see that our y equation becomes something we can work with. And so we find that it's going to become v naught times d over v naught cosine theta. You have to remember that there's a sine of theta here. So I said tangent because I'm thinking about what we're going to do here, which is turn the sine over the cosine into the tangent, but we'll do that in a second. And then minus 1/2 g, and then we have to take this junk and square it, right? So it should be quantity squared. And then it's just a matter of, cleaning this up. So let's see what we can do. Just keep this on the same line. We'll see that. So here, the v naughts cancel, right? And we can turn this sine over cosine into a tangent. So we find d tangent theta here. The other part doesn't really clean up that nicely, but it's fine. This will become g d squared over 2 initial squared cosine squared of theta, right? So this is our equation. Let me restate it because this is kind of cluttered. We find that h equals, and then all we really care about is this, right? Because this is the result that we're going to work with. We find that h equals this. And we have all the information we need to solve this, right? So I will go ahead and do well, rather, I'm going to have the computer do the algebra here. Actually, wait, I think I wrote this down. So let me just say then, I'm going to state the result and leave it as an exercise for you to show this. But we should find this kind of nasty expression that V initial should equal the square root of G times D over the square root of 2D tangent of theta minus 2H cosine of theta. No, sorry, the cosine should not be under the square root. Let me fix that. Cosine should be out here, okay? And actually, I did calculate the number here, looking at my notes here. So I found that this was going to be 15.6 meters per second. But again, I don't care about the numbers, right? And I'll mention this in recitation, but as far as homework assignments go, if you want to do the extra credit and work all symbolically, I don't even care if you plug the numbers in. I would go as far as to say that I prefer that you didn't plug the numbers in, just to emphasize my intense dislike of numbers. But anyway, this is what you should find numerically. I think some people are, they find some security in plugging something into their calculator and getting the same result, or the result that they think they're supposed to. So there's nothing wrong with that, right? It's fine. Okay, we're going to do one last example here. Hopefully this was clear and it helped you understand sort of the procedure for solving problems like this, these two-dimensional kinematics problems. The last one I'm going to do is not really even so much a problem as it is a derivation. And what we're going to do is we're going to derive an expression for the horizontal range of a projectile, which I'm going to call big R, that's launched at an angle theta above the horizontal with initial velocity v naught. And we have to assume here that the projectile is launched from and lands on flat ground. So its y initial is 0 when its y final is 0, or to put it another way, it's delta y is 0. So what we're really thinking about is sort of this exact thing, right? And our range is just going to be the distance from here to here, right? Where the projectile starts to where it lands. And this is a very useful result. So I think this is going to be a good example. Okay. So how do we begin this? The first step is almost always, right, the 2D kinematics problems, because I think 2D projectile motion is a little redundant. So the first step is usually going to be to break the velocity, initial velocity. Into components. And this is going to be nothing surprising. I assume at this point we're just going to find that that the x component is just v naught cosine theta, and the y component is v naught sine theta. But we can also actually write another thing here. We can write that this equals the x component at any time, right? Because one of our sort of results from looking at projectile motion was that the x velocity is constant, okay? So that's all well and good. Then, kind of we want to, I would say that this is another sort of strategic thing you can do if you're looking at a problem, a 2D kinematics problem, you don't really know what to do. I think that in general, writing out the equation for the y position, it just seems to be useful in a lot of these problems. So let's do that. And this is just, I'm just going to put the generic equation in here and we'll adapt it to our needs. We're going to say this, right? And I will say that the total time this is going to take, we'll call big T, right? That's usually my convention, is to say, if talking about some process, the total time it's going to take will be symbolized by a capital T. So let's put that in. And we're going to note that y of big T, right? That's 0 because we said that y initial and y final are 0, right? And again, that's just because the projectile is being launched from flat ground and it lands on flat ground. So we have y of big T equals 0. And we can, furthermore, right now, so this is my y of T. This is my y final, let's say, just so that's clear. Because I'm going to write another 0 here, and that's just because we're going to take the initial position of the projectile to be 0, which again is I think a very sensible choice and something we can pretty much always do. We plug in what the initial y is. That's just v naught sine theta. We just have to make sure we write big T now instead of little t, because little t is a variable and big T is a number. And then we write minus 1/2 g big T squared. And I will clean this up in the same line. I'm going to get rid of this 0. And I'm going to rewrite this just in different order. Okay, so this is our y equation. And let's just stop for a second and think about what we know, right? Because I think this can be tricky for students who are not used to working symbolically. So I want to just go over this. So we're given, right, v initial in the problem statement, right? When it says, you know, it's launched at this angle with this velocity, that means we know these things. So we know v initial, and we also know theta, which tells us what sine theta is, right? But we don't know t, and that's, you know, that seems to be a theme here, right? Is we don't know the time, and there's a good reason for that, which is because time is often the thing that's going to link the x and y components of motion for us, because it's, well, technically it's relative, right? But not from the Newtonian perspective, which is what we're looking at this from. So so it's a good sort of I don't know, reference variable, let's say. Okay, anyway, enough about the philosophy of physics. This, I think, is all we need for the y direction. So, you know, now we're kind of like at this point where we have, let's see, we have this unknown in our equation that we can't get rid of. Well, we can get rid of it, but we haven't gotten rid of it yet. So the way that we go about this then is we think about the x direction, and this is exactly what we did in the last example, right? So I'm just going to write that. Recall that we wrote that v initial x, and I know that I wrote this just up there, but I want to harp on this, right? That the x component of the velocity is constant. It's just v naught cosine theta. And from one of our kinematics equations, we can write something like this, right? Remember back to the previous lecture where I defined a generic velocity as being a displacement over time, right? And this means that applying this definition, which we can apply because the acceleration is 0 in the x direction, is going to tell us that v initial cosine theta, and I'm just going to change the notation here, but it's the exact same thing, right? Is just the range, which is our delta x, the horizontal range, over the time interval, which is big T. And this finally gives us that big T equals big R over v naught cosine theta, okay? So as before, we substitute this into our y equation. So let's do that. And it seems like the only difference between this and the previous problem is that now we have something we have basically the same equation, but in this case it's equal to 0 as opposed to before where it was equal to the height of the goalpost, right? But I'm going to get rid of this. This is the equation we want to work with. We're going to substitute in that big T is big R over V naught cosine theta. We'll do that over here, obviously, as well. And we find that our tangent theta minus G big R squared over 2 V naught squared cosine squared of theta, slash in there, is equal to 0, right? Because that's our final Y position. And I'm not going to do the algebra here. I'll let you work that out, but I can give you some ideas about how to proceed. Whenever we have an equation where one side is 0, we can do things like we can multiply both sides by some variable or some form of the variable, right, to sort of clean the equation up. And it looks like here maybe if we multiply both sides by 1 over r, which is equivalent to dividing both sides by 1 over r, we get a simplification, or we're going to have the equation look a little bit nicer, and we can then solve it. I don't think that has to be your approach here, but that would be one strategy. We like equations where some things are equal to 0 because that gives us a lot of freedom to manipulate them algebraically, right? Anyway, I'm going to just state the result here, and also remind you of one of the trig identities that's important. So upon solving this for r, we find, and let's see here, we find that the horizontal range is going to be v initial squared over g. And when you go through and do the algebra, you're going to wind up with something like this. You're going to wind up with, well, let me write it the way you'll probably write it, which would be like this. 2v naught squared, and then over here we're going to have sine of theta, and then we're going to have cosine of theta. But remember that one of our trig identities, the double angle identity, tells us that 2 sine theta cosine theta is just sine of 2 theta, right? So we can clean this up and write v initial squared over g times the sine of 2 theta. And that's our result. So, and now you can feel free to use this, on homework or on exam if you need to, that the range of a projectile, right, the horizontal range, if we know its initial velocity and the angle from which it is launched with respect to the horizontal, we can solve for the range. I do just have to remind you one more time, though, that this is only going to work if our delta y is 0. Right, because that was one of our big assumptions here as we went through and got this result. I am tempted to show you what the result looks like, and I think I will do this actually as the last thing we do. For the case where we don't have that delta y is 0, right? I'll do this after I just say a few words. And I want to just stress this because the students love this equation. They see it and they're like, oh my God, this is so useful. It's like the God equation, right? It can do everything. But it's only going to work if our delta y is 0. So don't forget that, please. I'm going to, as the very last thing here, just stop sharing. I'm going to move this over. And then I'm going to show you what this equation looks like when we can't assume that delta y is 0. Where'd my share screen go? There we go. I want to show this. So this nasty thing, right, is how it works out if we, and this is still assuming that y final is 0. It's just assuming that y initial is not. And so you could, I don't know, if you're really bored, try to derive this, but we won't need anything like this in this class. Okay, that's it. Hopefully this was helpful. You know, as always, feel free to reach out if you have any questions. If you want to ask anything before Monday when I force you to ask questions, just hit me up. All right, see ya.